I'm professor in high-performance computing at KTH, the Royal Institute of Technology in Stockholm, Sweden. And I'm currently here at the Baltic HPC conference in Riga, where we discuss the latest advances in HPC in the Baltic area, where, as Sweden is a neighboring country over the Baltic Sea, we're very much interested in. I'm also running PDC, which is the supercomputing center at KTH, and we are currently operating the largest machine in the Nordic countries, which is a 2-petaflop Cray machine. And as such, we are very interested in what the future in HPC brings, both from an architectural point of view, but of course also what this means for our users, for our applications. We are a generic data center. We are supporting all of Swedish academia and via the PRAISE project also European researchers in their HPC needs. And recently we started to investigate particularly what the movement towards even more powerful machines approaching the exascale will mean for our users. Many people think that exascale is just for the few big guys that can afford it, but in reality the technology that is being used for exascale is the technology that we will use at KTH as well. There will be no difference. So whatever the technology will be, we need to make sure that our users are prepared for that technology. And we know certain trends. We know that we have to go for more energy efficient hardware, which means that we will have less powerful cores, but more of them. We know that we will go into deeper memory hierarchies and so forth. So there is big challenges ahead of us, and we started to work in various contexts to approach these challenges. I'm very happy that the European Commission actually has taken stake in these developments and has launched previously already a set of flagship projects towards exascale under FP7, and now in Horizon 2020 a new round of FET HPC projects. This is also how we got into this field. We participated in the CRESTA FP7 exascale flagship project, where we work particularly with two codes of big importance for Swedish researchers, GROMACS and NEC 5000, which is molecular dynamics and CFD codes, to explore what the bottlenecks are, to further scale them, to make them efficient on future architectures. And we are now carrying this work forward in a variety of FET HPC projects. Particularly, we are launching in October a project called Exaflow, which deals with exascale algorithms for fluid dynamics. So we are trying to have a holistic view of the problem, approaching the exascale problem from the algorithmic point. What algorithmic concepts will be needed to exploit exascale architectures efficiently? How do you deal with error control? How do you deal with fault tolerance? How do you deal with adaptivity? Then, of course, once we have the algorithmic formulations, how can we efficiently implement them? What programming paradigms do we need? What will be the middleware that we will be using? And we are also running a couple of projects that deal with those aspects, like the Epigram project, which is now already in its second year, is looking into bottlenecks that classical MPI applications have, and whether MPI can actually be made ready for exascale, which is something that we clearly believe in. But we don't think that MPI will be the only solution. You will need different mechanisms. We are particularly looking into BGAS-based approaches, specifically the GPI BGAS library developed by Fraunhofer. See how a combination of MPI and BGAS approaches can actually help towards exascale. This work is also carried forward in a new project called Intertwine, led by EPCC in Edinburgh, that is looking into the interoperability issues of different programming approaches, like MPI, like threads, component-based programming, and so forth, which is a very important aspect as we approach exascale, because Exascale systems are likely to be so heterogeneous and difficult to use that there will not be one single model that will be sufficient to exploit the machine to a full extent. Another very exciting activity that is just starting is the Centers of Excellence in HPC. That's a new concept where we try to make not only efficient software, but also make this software maintainable, sustainable, and available to the researchers, to users both in academia and industry. So here we really try to provide support to users of software in which software to choose, which hardware to choose, how to set up the application, the experiment in a most efficient way. We're starting one of these centers of excellence in HPC in the biomolecular area, in the life sciences, in autumn this year, where we will be particularly targeting the pharmaceutical sector, for instance, but also the food sector, in their approaches to develop new drugs, to develop new concepts for nutrition, and in the biomolecular simulations that they need for that. Summarizing, I think the challenges that we have ahead of us that are posed by the Exascale development, but that will be challenges for all of us, not only the ones that really have Exascale class problems. They are so huge and so difficult to solve that we really need international efforts to do that. We need efforts on the European scale, and I alluded to some of the European efforts here, but we also need to work together with our colleagues in the US and in Japan and in other places of the world, but also in regional settings, like here in the Baltic countries, where we need to make sure that knowledge, technology, practice is being transferred and independent where researchers are, they have access to the best breed of software, the best breed of hardware, and the best breed of technology.